According to the National Electrical Code, there is a preferred color code for receptacles powered by uninterruptible power supplies, or UPSs. NEC 2020 Article 700.8e states that receptacles supplying power from a UPS must have a distinctive color that differs from normal circuit conductors. The NEC doesn't specify a particular color, however, the following colors are commonly used: brown, orange, yellow, and red. These colors are not typically used for normal circuit conductors. Therefore, they can easily identify UPS-powered receptacles. The reason for a distinctive color code is to help prevent unintentional disconnection of UPS-powered equipment during maintenance or emergencies, especially when normal circuit breakers are opened. By using a different color, personnel can quickly identify and avoid disconnecting UPS-powered receptacles. The color code should be applied to the faceplate, cover plate, or the visible portion of the receptacle. It's not necessary to color code the entire circuit, only the receptacles that are powered by the UPS. If multiple UPS are used, different colors can be assigned to each UPS to further enhance identification. For typical branch circuit wiring, the ungrounded conductors, or hot wires, are black, red, and blue. The grounded conductor, or neutral wire, is white or gray. The grounding conductor, or ground wire, is green or bare. These color codes are standard in North America and help electricians easily identify the purpose of each wire. When working with electrical systems, safety is paramount. Here are some essential safety precautions to keep in mind. Firstly, always to energize the circuit before working on it. Turn off the circuit breaker or remove the fuse that supplies power to the circuit you'll be working on. Use a voltage tester to confirm that the circuit is de-energized. Secondly, use insulated tools. Use tools with insulated handles to prevent electric shock. Ensure the insulation is in good condition and free of cuts or tears. Thirdly, wear personal protective equipment, or PPE. Wear safety glasses to protect your eyes from debris. Wear rubber gloves to insulate your hands from electrical current. Fourthly, be aware of your surroundings. Work in a dry area and avoid contact with water or moisture. Keep your work area clean and free of clutter. Fifthly, follow lockout, tagout, or loader procedures. If you're working on a circuit that could be energized by someone else, use loader procedures to prevent accidental energization. Place a lock and tag on the circuit breaker or disconnect switch to indicate that the circuit is being worked on. Sixthly, double-check your work. Before restoring power to the circuit, double-check your connections to ensure they are tight and secure. Make sure all wires are properly insulated and there are no exposed conductors. Seventhly, test your work. After restoring power to the circuit, test it to ensure it's working properly. Use a multimeter or other testing device to verify voltage, current, and continuity. Eighthly, know your limits. If you're not comfortable working on a particular electrical task, don't attempt it. Call a qualified electrician to do the work for you. Ninthly, follow the National Electrical Code, or NEC. The NEC provides detailed guidelines for safe electrical installations. Familiarize yourself with the NEC requirements for the type of work you're doing. Tenthly, stay alert and focused. Avoid distractions and concentrate on the task at hand. Electrical work requires attention to detail and a clear mind. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for safe electrical installations in the United States. It's published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It's used by electricians, electrical inspectors, and other professionals to ensure that electrical systems are installed and maintained safely. Some key articles within the NEC include Article 210. This article covers branch circuits, which are the circuits that supply power to outlets, lights, and other devices. It includes requirements for the number of outlets on a circuit, the size of the wire, and the type of overcurrent protection. Article 250 covers grounding and bonding, which are essential for electrical safety. It includes requirements for grounding electrodes, grounding conductors, and bonding of metal parts. Article 300 covers wiring methods, which are the ways that wires are installed and protected. It includes requirements for conduit, cable, and other wiring methods. Article 400 covers flexible cords and cables, which are used to connect portable appliances and equipment. It includes requirements for the type of cord, the size of the wire, and the strain relief. Article 430 covers motors and motor circuits, which are used to power machinery and equipment. It includes requirements for motor protection, motor controllers, and motor wiring. Article 500 covers hazardous locations, which are areas where flammable gases, vapors, or dust may be present. It includes requirements for equipment and wiring in these locations. Article 600 covers electric signs and outline lighting, which are used for advertising and decoration. It includes requirements for the type of sign, the wiring, and the overcurrent protection. Article 700 covers emergency systems, which are used to provide power during a power outage. It includes requirements for generators, transfer switches, and emergency lighting. To effectively use the NEC, firstly, understand the scope and purpose of the NEC. The NEC is intended to provide practical safeguards for persons and property from hazards arising from the use of electricity. Secondly, familiarize yourself with the NEC organization. The NEC is divided into chapters, articles, and sections, each covering a specific topic. Thirdly, learn how to navigate the NEC index. The index is a valuable tool for finding specific information within the NEC. Fourthly, use the NEC tables and examples. The NEC includes numerous tables and examples to help illustrate the requirements. Fifthly, stay up to date with the latest edition of the NEC. The NEC is updated every 3 years, so it's important to use the latest edition. Sixthly, consult with a qualified electrician or electrical inspector. If you have any questions about the NEC, consult with a qualified professional. When selecting wire size, several factors must be considered to ensure safety and compliance with electrical codes. These factors include ampacity, voltage drop, and insulation type. Ampacity refers to the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables that list the ampacity of different wire sizes and insulation types. Voltage drop refers to the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Insulation type refers to the material that surrounds the conductor and provides electrical insulation. Different insulation types have different temperature ratings and are suitable for different applications. The NEC specifies the types of insulation that are permitted for different wiring methods. To determine the appropriate wire size, firstly determine the load current. Calculate the amount of current that the circuit will be expected to carry. This can be done by adding up the wattage of all the devices that will be connected to the circuit and dividing by the voltage. Secondly, select the appropriate ampacity. Choose a wire size that has an ampacity greater than or equal to the load current. Refer to the NEC tables for ampacity ratings. Thirdly, check for voltage drop. Calculate the voltage drop for the selected wire size and length of the circuit. If the voltage drop exceeds the recommended limits, increase the wire size. Fourthly, select the appropriate insulation type. Choose an insulation type that is suitable for the application and meets the NEC requirements. Fifthly, consider dirting factors. If the wire will be installed in a hot environment or in a bundle with other wires, it may be necessary to dirt the ampacity. Refer to the NEC for dirting factors. Electrical conduit is a protective tube or channel used to enclose and protect electrical wiring. It's typically made of metal or plastic and is available in a variety of sizes and types. Conduit is used in both residential and commercial buildings to provide a safe and reliable pathway for electrical wiring. Different types of electrical conduit are firstly, rigid metal conduit, or RMC. This is a heavy-walled steel conduit that provides excellent protection for wiring. It's typically used in exposed locations or where there is a risk of physical damage. Secondly, intermediate metal conduit or IMC. This is a lighter weight steel conduit that offers similar protection to RMC. It's often used in place of RMC to reduce weight and cost. Thirdly, electrical metallic tubing or IMT. This is a thin-walled steel conduit that is easy to bend and install. It's typically used in concealed locations or where there is no risk of physical damage. Fourthly, flexible metal conduit or FMC. This is a flexible steel conduit that can be bent around obstacles. It's often used to connect equipment that vibrates or moves. Fifthly, rigid polyvinyl chloride conduit or PVC. This is a non-metallic conduit that is resistant to corrosion. It's typically used in underground or wet locations. When selecting electrical conduit, consider firstly the environment. Choose a conduit that is suitable for the environment in which it will be installed. For example, use PVC conduit in wet locations or RMC conduit in exposed locations. Secondly, the size of the wires. Choose a conduit that is large enough to accommodate the wires that will be installed in it. Refer to the NEC for conduit fill requirements. Thirdly, the type of equipment. Choose a conduit that is compatible with the equipment that will be connected to it. For example, use flexible metal conduit to connect equipment that vibrates or moves. Fourthly, the cost. Consider the cost of the conduit and the labor required to install it. Choose a conduit that is cost-effective for the application. Overcurrent protection is a critical safety feature in electrical systems. It's designed to protect wiring and equipment from damage caused by excessive current flow. Overcurrent protection devices, such as circuit breakers and fuses, interrupt the flow of current when it exceeds a safe level. Circuit breakers are electromechanical devices that trip and interrupt the circuit when an overcurrent occurs. They can be reset manually after the fault has been cleared. Fuses are one-time use devices that melt and interrupt the circuit when an overcurrent occurs. They must be replaced after they have blown. Overcurrent protection devices are rated in amps, which indicates the amount of current that they can carry before tripping or blowing. It's important to select the correct size overcurrent protection device for the circuit to ensure that it provides adequate protection. To select the right overcurrent protection, firstly determine the load current. Calculate the amount of current that the circuit will be expected to carry. This can be done by adding up the wattage of all the devices that will be connected to the circuit and dividing by the voltage. Secondly, select the appropriate overcurrent protection device. Choose an overcurrent protection device that has an amp rating greater than or equal to the load current, but not greater than the ampacity of the wire. Thirdly, consider the type of load. Some loads, such as motors, require special types of overcurrent protection devices. Refer to the NEC for requirements for specific types of loads. Fourthly, coordinate overcurrent protection devices. If there are multiple overcurrent protection devices in a circuit, they should be coordinated to ensure that the device closest to the fault trips first. Electrical grounding is the process of connecting electrical equipment and systems to the earth. Grounding provides a low resistance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. Grounding also helps to stabilize voltage and reduce electrical noise. There are two main types of grounding: equipment grounding and system grounding. Equipment grounding connects the metal parts of electrical equipment, such as enclosures and conduit, to the earth. This helps to prevent electrical shock if a fault occurs in the equipment. System grounding connects the neutral point of the electrical system to the earth. This helps to stabilize voltage and reduce electrical noise. To properly ground an electrical system, firstly, install a grounding electrode system. This typically consists of one or more ground rods driven into the earth. Secondly, connect the grounding electrode system to the equipment grounding conductor. The equipment grounding conductor is a wire that connects the metal parts of electrical equipment to the grounding electrode system. Thirdly, connect the grounding electrode system to the system grounding conductor. The system grounding conductor is a wire that connects the neutral point of the electrical system to the grounding electrode system. Fourthly, bond all metal parts of the electrical system together. Bonding is the process of connecting all metal parts of the electrical system together to create a low resistance path for fault current to flow back to the source. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electrical shock. They work by monitoring the current flowing in a circuit and detecting any imbalances that could indicate a ground fault. If a ground fault is detected, the GFCI quickly interrupts the flow of current, preventing a potentially fatal shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. They are typically installed in outlets or circuit breakers. To test a GFCI, press the test button on the GFCI device. This should trip the GFCI and interrupt the flow of current. If the GFCI does not trip, it should be replaced. To reset a GFCI, press the reset button on the GFCI device. This will restore power to the circuit. Electrical bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current to flow back to the source. Bonding helps to prevent electrical shock and fire hazards by ensuring that all metal parts are at the same electrical potential. Bonding is required by the NEC in many locations, including service panels, equipment enclosures, and metal piping systems. To properly bond an electrical system, firstly, use bonding jumpers to connect all metal parts together. Bonding jumpers are short lengths of wire or metal straps that are used to connect metal parts together. Secondly, ensure that bonding jumpers are properly sized. The size of the bonding jumper should be based on the size of the circuit conductors. Thirdly, use approved bonding connectors. Bonding connectors are used to connect bonding jumpers to metal parts. These connectors must be approved for use in electrical systems. Electrical overloads occur when a circuit is carrying more current than it is designed to handle. Overloads can cause wires to overheat, which can lead to insulation damage, fire hazards, and equipment failure. Overloads can be caused by a variety of factors, including too many devices connected to a circuit, faulty equipment, and undersized wiring. To prevent electrical overloads, firstly, avoid overloading circuits. Do not connect too many devices to a circuit. Secondly, use properly sized wiring. Ensure that the wiring is sized appropriately for the load. Thirdly, use overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, will interrupt the flow of current if an overload occurs. Electrical short circuits occur when there is an unintended connection between two conductors with different potentials. Short circuits can cause a large amount of current to flow, which can lead to rapid heating, explosions, and fire hazards. Short circuits can be caused by a variety of factors, including damaged insulation, loose connections, and foreign objects. To prevent electrical short circuits, firstly, use proper wiring techniques. Ensure that wires are properly insulated and connected. Secondly, protect wiring from damage. Protect wiring from physical damage, such as cuts and abrasions. Thirdly, use overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, will interrupt the flow of current if a short circuit occurs. Electrical arcing is the flow of current through the air between two conductors. Arcing can generate intense heat, which can ignite flammable materials and cause explosions. Arcing can be caused by a variety of factors, including loose connections, corroded contacts, and damaged insulation. To prevent electrical arcing, firstly, use proper wiring techniques. Ensure that connections are tight and corrosion-free. Secondly, protect wiring from damage. Protect wiring from physical damage, such as cuts and abrasions. Thirdly, use arc fault circuit interrupters, or SIs. SIs are designed to detect arcing and interrupt the flow of current, preventing fires. Electrical fires are fires that are caused by electrical problems. Electrical fires can be caused by a variety of factors, including overloads, short circuits, arcing, and faulty equipment. To prevent electrical fires, firstly, follow all electrical safety precautions. Secondly, use properly sized wiring and overcurrent protection devices. Thirdly, inspect electrical systems regularly. Look for signs of damage, such as frayed wires, loose connections, and burned components. Fourthly, have electrical work performed by a qualified electrician. The National Electrical Code provides specific guidelines for wiring different types of equipment. For lighting fixtures, the NEC requires that lighting fixtures be properly supported and grounded. It also specifies the type of wiring that can be used and the minimum size of the conductors. For appliances, the NEC requires that appliances be properly grounded and protected by overcurrent protection devices. It also specifies the type of wiring that can be used and the location of the disconnect switch. For motors, the NEC requires that motors be protected by overcurrent protection devices and that the motor controller be properly sized. It also specifies the type of wiring that can be used and the location of the disconnect switch. For heating equipment, the NEC requires that heating equipment be properly grounded and protected by overcurrent protection devices. It also specifies the type of wiring that can be used and the location of the disconnect switch. For air conditioning equipment, the NEC requires that air conditioning equipment be properly grounded and protected by overcurrent protection devices. It also specifies the type of wiring that can be used and the location of the disconnect switch. When working with electrical panels, firstly, always to energize the panel before working on it. Turn off the main circuit breaker that supplies power to the panel. Use a voltage tester to confirm that the panel is de-energized. Secondly, wear personal protective equipment or PPE. Wear safety glasses to protect your eyes from debris. Wear rubber gloves to insulate your hands from electrical current. Thirdly, be aware of your surroundings. Work in a dry area and avoid contact with water or moisture. Keep your work area clean and free of clutter. Fourthly, identify the circuits. Before working on a specific circuit, identify it by tracing the wires back to the circuit breaker. Label the circuit breaker with the circuit number and description. Fifthly, use insulated tools. Use tools with insulated handles to prevent electric shock. Ensure the insulation is in good condition and free of cuts or tears. Sixthly, follow lockout, tagout, or LOTO procedures. If you are working on a panel that could be energized by someone else, use LOTO procedures to prevent accidental energization. Place a lock and tag on the main circuit breaker to indicate that the panel is being worked on. Seventhly, double-check your work. Before restoring power to the panel, double-check your connections to ensure they're tight and secure. Make sure all wires are properly insulated and there are no exposed conductors. Eighthly, test your work. After restoring power to the panel, test it to ensure it's working properly. Use a multimeter or other testing device to verify voltage, current, and continuity.